lengths and curvature. This chapter is actually not too bad. I think you will like the homework. My most favorite is 10.9. Actually, the last one is really nice. I like velocity, acceleration, so that comes right after that. So we're almost done with the chapter 10, learning about vectors. We did not cover yet the arc length and curvature. Here's a nice graph, and just like in calculus 1 and 2, we were teaching you this classical formula. That's not new. Square root, derivative square plus derivative square, and that's integral from a to b. That's arc length before we went to vectors. So that's just a fact. We're reviewing it. How long is a snake? Remember, I was showing you, what if we have a snake and originally you think you make it flat and measure, but what if it wants to bite you? How do you do that? What we did, we were approximating a snake with these segments, and then we were adding them together, infinitely many, and they shrink in size, gives you the Riemann sum, and then that becomes the integral, square root, derivative square plus derivative square. So that's what we're going to do. Now we have vectors though. Suppose that the vector, we have a vector equation, like we learned before, and the curve is traversed. If the curve is traversed, what is traversed? Do you know the word traversed? What is that?
Traveled.
Traveled, exactly. Thank you. I like asking. Traversed means traveled exactly once as t is increasing from a to b. Then we have basically the same equation. That's a beautiful thing. That is not many things to learn in this case. So L is derivative square plus derivative square plus derivative square. We have 3 dimensions. In this case, what's new is, now let's call it R. Well, it's not just that. It's not just that is new. What is new is, no, don't. Sorry that I touched you. Wow. Come on. You can do it. So integral, you can write down integral square root derivative square plus derivative square plus derivative squared. And R is, in this case, it's a vector equation. Inputs are numbers, in this case are even functions. Outputs are what? Vectors. That's a new thing. So inputs are real numbers. Outputs are vectors. That's called vector equation. Vector equation. EQN is my notation for equation. Who is talking so much? I can hear you, and it's very distracting. Thank you. My English translator cannot stop just because you're whispering. So I have to, it automatically translates what you're whispering, and it's very distracting. It's hard to control that. That's why I cannot listen to TV and talk to someone at the same time. It's very distracting. So, you see, so that's actually not very something new. What is absolute value here? What is that? Vector what? Magnitude, yes, good job. So that's magnitude. So in this case, we're just going to do that. Here it is. Yeah, there's some construction going on behind the door, so if it distracts you, you should move to the front. They're fixing the door, and it smells very bad. So here it is. It's exactly what we did before. It's picture in 3D, so draw it. It's actually very pretty. In blue, it's a nice curve, right, from A to B. And what they do now, or we do, we're approximating with those segments again, like so. And so on, and then they adding infinitely many of them, blah, 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 and stuff like that. That gives us an integral. So we're just going to practice finding all of this. That will be your favorite question on the exam, because it's the same problem we had in calculus 2. We're just renaming it using vectors. But the problem is the same. Let's do it. So, find the length of the helix from 0 to 6 pi. So I want to find, I think there's an animation here, helix 2. Yeah, it says that. Yeah, that's what I was showing you at the beginning of the class. Here's the helix, right, or spiral. Well, you see the object is traveling up, in this case, so it's counterclockwise or clockwise. That's always different, going up, going down. But then I want not the infinite one. I want to know how long it is for like the next 10 seconds or for this 5 periods of rotation. So in this case, where did my thing go? Ah, interesting. In this case, we want from t equals 0, t equals 6 pi. So we have rotations, and we want to calculate the lengths up until several rotations. Find the lengths of the helix r of t. R is a vector, remember that. 2 cosine 5t, 2 sine 5t, 3t. And then I want just several spins from t equals 0, t equals 6 pi. Spins mean, by spinning, I mean it's a periodic function, so several periods, right? That's what I mean here. Now, here's a nice sketch. Here is a helix. You don't have to draw a cylinder. That is just kind of to represent it in 3D because, you know, this kind of looks 2D. But, you know, it's a nice helix. It has height, and we can always describe height as z. Then it goes forward towards me. So we're going to describe that as x. And it goes to the right somehow. So we describe it as y. Like so. And we want only the lengths from t equal to 0, t equals 6 pi. So I will highlight this with yellow, I guess. We only want the lengths of this part. It is infinite, but we will only want that. If you see from the example, from the equation, I would say, it says 3 cosine, 2 sine, and 3t. So this z is increasing to plus infinity and minus infinity. So it's a z's height. So it's infinitely long helix. But we only want from when t0, t6 pi. Let's do it. Just kind of basically plug in into example, to the formula solution. I guess I should go down below. That's a wrong note. I see. Here it is. Yeah, much better. Solution. Your job basically to know the formula. L equals integral from a to b, and we literally gave it to you. 0 to 6 pi. A huge, gigantic square root. And then derivative squared plus derivative squared plus derivative squared. So if you know the formula, you already can do the multiple choice question. Usually that's multiple choice question, unless it's not. Yes?
We're not going to be allowed calculators on the test.
You can. You can use graphing calculators on test.
Okay.
That's why they are in the syllabus. They even like a list which one you're allowed to have and which one you're not allowed to have. No, you basically, yeah, calculators is the best part of the exam. You can have that. And you have your own, you feel safe with it. It's your friend, so it feels good. So what I'm talking about, derivative squared, I'm quickly finding derivatives of what I see in front of me. That's what I'm doing here. 2 cosine 5t is minus 2 sine 5t. Yes or no? What's missing? 5. Times 5. So it's 10, right? Don't forget chain rule. Good job. Chain rule. People remember. So people who just missed what happened, let's concentrate right now. What's happening with 2 sine 5t, derivative of sine is cosine. So I'm claiming it's going to be 2 cosine 5t, but then times derivative of the function inside, which is 5. So 5 times 2 is 10. Finally, the last one is easy. 3t gives you 3. Derivative squared, derivative squared, derivative squared. Like so. Simplify, integrate. So you just need to know the formula. It's not even different from the formula we had in calculus 2. We just added more dimensions to it. You can have 5 dimensions, and it's still going to be the same arc length. You're just going to... it's all proven using right triangles anyways. It's coming from the Pythagorean theorem. So let's simplify. Integral from 0 to 6 pi. Minus 10 squared is 10 squared outside. Sine squared 5t plus 5t. Tan squared cosine squared 5t plus 9. What do you notice? Do you notice anything good? Does it make you feel good somehow? Exactly. Sine squared plus cosine squared is 1. So they just factor out tan squared. And that's usually people don't do it with writing. It's too much writing. So they just do it in their head. 0, 6 pi. Square root is not going to be huge anymore. Tan squared was factored out, and it's going to be 1 plus 9. Because, let me rewrite for you. Sine square of theta plus cosine square of theta is 1. And theta can be any, it just have to be the same. So it's 5t and 5t, that's what helped. So it's 109 inside of the square root. Integrate that and you're done. Do you know how to integrate fast if you only end up with a constant? You can write down square root of 109, 0.6 pi dt. That's what I like to call naked integral. There's nothing inside. Well, there's 1 inside. So you plug the top minus the bottom into t. But actually, there's a nice understanding that if there's no function inside of the integral, then the answer will be the length between a and b. The length between 6 pi and 0. So it's just 6 pi. So the answer is square root of 109 times 6 pi minus 0, which is 6 pi. That's the answer. This is how long the helix was from 0 to 6 pi. Does that make sense, people? Yeah, so this is a good one. Questions, ideas, suggestions? Okay, good. Moving on. What does it mean to have a smooth curve and not a smooth curve? Remember in calculus 1 we taught you that you have cusp with a weird word, cusp, basically sharp corners. Then derivative does not exist here. F prime is not defined, D and E, at cusp corners. So smooth is looking like so. All derivatives are defined. Not smooth, derivative is defined, boom, like what's going on here. You cannot define a derivative at the cusp because the switch between the slope is too fast. This one switches the slope quite carefully, while this one was nice and then somehow switched almost perpendicularly. So the derivative of that doesn't exist. That's why I have this cute animation. I show it to business students. They liked it a lot. When we teach increasing, decreasing, maximum, minimum, I show it to business students. I think they liked it. It's an alien duck. I don't know why and who created it, but I feel like it's genius. As you can see, derivatives are 0 at the max and means, negative and positive. So we know that. Now, smooth. That's lots of definitions. I can just give you the notes, so you don't have to write them down. But a curve is smooth if it has a parameterization x and y, f of t and g of t on the interval I, such that, guess what? Derivatives exist everywhere. They are continuous. Derivatives are continuous, not simultaneously 0, except maybe at endpoints. The curve is piecewise smooth if it's smooth in the pieces. So it was smooth. Where's the graph? It was smooth here and here and here, piecewise, but not in between. So that is the definitions here. You will see it in lots of applications. Because engineers and physicists, they keep building things. So I like to show some kind of applications in medicine because I like that. I feel like it's very interesting that our body has lots of calculus in it. As you can see, that's also a good example of a smooth curve. Luckily, it's smooth unless you break your spine, then it's not going to be smooth anymore. Be like, pfft. Yeah. So note, a smooth curve will have no corners or cusps. So that's basically what I wanted you to know. It's smooth, then it's smooth. How curved a line or surface is, how much the curve varies from being straight to flat. Now here's the question. This is what curvature is. It's a very cool question. Okay, so the curve is smooth, but how smooth? So smoothness also can be kind of explained. very smooth. Like if you're hiking this, you're very happy about it. And then it's like not very smooth. So, and then it's getting worse. And then if you do rock climbing, does anyone here do rock climbing? Right? So you know, then it's like, what is that? Then, so how smooth or not smooth things are, that's called curvature. So let's draw this picture. This is actually a pretty cool picture. Here's the curve. I will put it in purple. Here's the curve. Don't make it the same. So the first curve is big and smooth, and the second one is smaller. So high curvature means it's curved highly, right? Does my English make sense? So curvature, how much curved it is. Curving is bad. Something that curves too much, it's hard to describe. Heartbeats, and this is hard to describe. While waves in the ocean, they're huge, and if it's not a storm, they have low curvature. So the way to describe it is actually really clever. If you make a circle below or above this curve part where it's curved, will the radius be big or small? So for the first case versus the second case, you can see that the radius is different. That's what we call radius of the curvature. The radius of the curvature and the center of the curvature will tell you if the curve is curved a lot or not. That's kind of how interesting this idea. When I was learning for the first time, I found it's pretty clever. The ball on this curve is sitting. How big is that ball? How big is the circle describes the curvature. And that has so many applications in physics and everywhere. It's very important. So we're going to be discussing and describing curvatures. So for example, if now the hike, so imagine you're hiking, right? Smooth hike has big radius of the circle. This is a hard hike. So the small circle indicates high curvature. It's curved highly. And then look at this, like drop. Let's see how tiny the circle will be here. Here, how small it is. That is very curved. So it's going to be high curvature. Isn't cool? So, and of course I can make it very smooth. Then this circle is huge. And it's there, not falling anywhere. It's not rolling away if it's a ball. That will be a huge radius. Yes?
So isn't the only time when it doesn't have a derivative, isn't that only when it's
oh, good question.
Super sharp curve?
The question is is there more ways to know when derivative doesn't exist? Sharp corners, have to be very sharp though.
Yeah, like that.
And discontinuities, jump from here to here, remember? Infinities, so vertical, horizontal asymptotes. This is where also derivatives do not exist. But if it's continuous, then it's a cusp. Yeah. There's one more. When the function is continuous. So the functions keep going. Why would derivative stop existing? Because of these kind of sharp corners. And there's one more rare case when derivative is infinitely wiggling. There's very cool examples about that. Then also not the derivative. The original function is wiggles too much. Then the derivative cannot decide where to stop. That's one more case called infinite discontinuities. Yes. Actually.
So the relationship is basically the more radius, the more smooth.
The more smooth, exactly. So let's write down some cool stuff after that. The cool stuff is, well, now you have the spine here, which is cool. Oh yeah, let's see actually, interesting. So scoliosis is not as bad as kyphosis, right? Because this circle is pretty big, right? So it is tilted, curved, but not too badly. You can still live like that. Most of you probably have that because you're STEM majors and sitting at the computer all the time and studying, right? Like, am I wrong here? Computer scientist? Good luck with that. And then look how small this circle is. So that is a very curved one. That is actually health problems and everything. So for you to know, women getting older, the muscles they have here are getting weaker than the man muscles. So that's why you see more women with head going down, like so, because the spine cannot hold it anymore. So we need more vitamins, supplements because of that when we get older. Very interesting. I did not know that until recently. A curve is called smooth if it's a smooth, don't have to write this down. If it has a smooth parametrization, a smooth curve has no sharp corners. We already said that. What we want to say now is how to define a smooth curve is defined by the vector function r. Recall that there is a unit tangent vector. We also have it from last notes. Unit tangent vector, it's already on the test. Find the unit tangent vector. R prime over the size of R prime. And then it indicates the direction of the curve. So what's new is going to be a curvature. A curvature. So let's write this down. Let's define the curvature. We define the curvature to be the magnitude of the rate of change of the unit tangent vector with respect to the arc lengths. What? So let's write down the definition and then check what it means. So curvature will tell us high curvature, bad. That means it wiggles a lot. Bad. Low curvature means it doesn't really curve too much. That's good. That's like very smooth. So you imagine either the hike is very easy when there's low curvature, or the waves are peaceful. And then we're defining it as a magnitude, which is just a size. Of what? Rate of change, that's a derivative. A size of the derivative, or magnitude of the derivative. Of what? Of the unit tangent vector that was derived with respect to the arc lengths. Okay, well, that's a lot to memorize. Let's figure this out. K. Usually it's a cursive K. K is a unit, here's the, you don't have to write the parentheses here. That's just a note. We use arc length so that the curvature will be independent of the parameterization. So, arc length tells us how long is the curve. Tangent tells us, like there was a duck that was traveling, how much the duck is traveling up and down. That's tangent. Every time you talk about any curve, even this funny one, right? Look at this. Those are all tangents. So tangents tells us how smooth it is. Is it smooth or it's not smooth, right? So they take how fast the tangent is changing, that's derivative of a tangent, with respect to the arc length, the length of the arc. And that gives us the curvature. Here it is. So write down K equals dt. T is unit tangent over ds. S is the arc length. And then we take absolute value of that, which is a magnitude. We're going to rewrite this so you will have easier ways to find it. In general, you can also find it in this way. It's going to be, we're using chain rule and everything, so the formula becomes easier. Take the derivative of the unit tangent vector. Tangent vector is already a derivative. So now we want to see how fast the derivative is changing. If you remember how fast the derivative is changing, it has something with concavity. That's exactly what curvature is. Concave, how concave up and down it is. Then take how fast r is changing. That's the arc. It's kind of arc length, but actually we're talking about the curve here. Take size of h, magnitude. And I will put double ones because I like that more, but you don't have to. So that is the formula. Let's practice that. And then we will have more formulas also coming from there. So let me show you. Put this in one more box, like so. Boxing, putting in boxes your answers and formulas is very nice because then you can find it easily in your notes. Color coding is also very important. When I was a student, I was color coding all my math notes. Theorems were red, examples were blue, properties were green. So when you go back before the final exam, you can find everything easily. So color coding is a thing. I was doing it before knowing it. Was actually a whole study about it. You don't have to write this down. The curvature is easy to compute if you express it in terms of the parameter t. So we use chain rule. And that's exactly how this formula was created. We just wrote it down. Chain rule is everywhere. For the special cases of the plane curve with the equations given, you can always rewrite it also this way. Yeah, that's like not easy to memorize, but second derivative is involved. That makes sense because second derivative is about concavity. Then let's write down this. We're probably not going to be using this formula, but it exists. Curvature can be found as a cross product of the first derivative and the second derivative divided by the first derivative cubed, and all of those are in sizes because we want a number. We don't want a vector. We want just a number. Is it a big number or is it a small number? That will tell us lots of information. Curvature. So that's one of the cool properties in new formula to memorize, unfortunately. And then we're going to practice it in a second after we defined more things. Today, lots of theory, more theory than actual examples. I will try to give more examples on Thursday. Now, let's introduce T and B vectors. So this one, was it too fast? R prime, cross product R prime prime over R prime cube. And then size of everything. So we're going to be collecting finally T, N, and B. Those are very important things in STEM. T, N, and B. T is a unit tangent vector, which we already had at practice at home in last homework. R prime over size of R prime. And will be the same idea with a normal vector, and it's going to be a B there. The idea is actually pretty fascinating. Let me show you a cool animation to wake you up. Go. Okay, well, it's not getting anywhere. Some of those links got deleted, so see ya. Okay, fine. There was one more. Okay, wow, okay, that's not what I wanted to show, but okay. That actually is explains some about curvature, how curves can be bigger and smaller. Check it out, how they're doing it. But what is definitely very interesting, I think I had it here. Oh yeah, here it is. This is what I wanted to show. Those three vectors are T and B. T and B. Tangent vector is in red. It touches the curve. It's called a kiss. Tangent is a kiss, basically. Then normal and binormal are sticking out, and they're all perpendicular to each other. Those three magical vectors describe everything. It's kind of like IJK, but it has more applications in physics, gravitational forces, aerodynamics, temperatures, everything. Because if you mention it's a rocket going up, tangent tells us how the rocket will go up. Normal vector perpendicular to tangent, usually some gravitational forces or wind that's trying to hit the rocket in other direction. And binormal has also lots of applications. So that's time to learn that. That's definitely for the STEM majors. It's very important for applied STEM majors specifically. So the normal binormal vectors, we already have T. Let me write down all three here. So just write down that T equals R prime over R prime. This is how it's easy to memorize it. And then it doesn't make sense because it's 1, so you take absolute value of the size. It's derivative, but without its size. I don't want to know the size of the tangent vector, so I unitize it. I find the unit tangent vector. Put this in the box. That's T. N is exactly the same thing, but now we're using T. Normal vector. Normal, which is unit normal vector. Sometimes it's called principal unit normal vector because it's important. Takes T prime over T prime. How cool is that? So now we take tangent normal and get rid of its size. And then the binormal vector takes both of them and finds a cross product. And if you remember, cross product is perpendicular to those vectors involved. So B is perpendicular to both. This is a famous T and B. In general, if you find a person who found a job as an engineer or physicist, you can ask them T and B, and people do remember it because it's actually applied everywhere. We define a principal unit normal vector and binormal vector this way. Here they are. We will be asking you to find all three, T and B. B is the time-consuming one, but T and N are extremely important and actually pretty fast to find. So they are all perpendicular to each other. This is a nice picture. Here's the curve. We have T. It's a tangent, so it's touching the curve, right? Then N is perpendicular to T. And B is perpendicular to both normal and binormal. They describe lots of things. So normal and binormal. T and B. This is how it looks in 3D. Each of them creates a plane. So these beautiful planes that can describe the curve, how smooth it is, how it's increasing, decreasing, going up, going down, and so on. Here's one more color-coded explanation. In this case, green is tangent. T and B are sticking out. That's probably where my... Okay, and the planes, you don't have to actually write this down. It makes sense. Each vector creates a plane. They call it, guess what? Tangent plane, normal plane, and binormal plane. So all the planes are there. So normal plane, binormal plane is fine, but tangent plane called oscillation plane because it actually tells you how fast something is changing. Let me just tell you that. This is very nice that I have good notes. Actually, yes, and the curvature is here. The plane determined by the normal and binormal vectors, N and B, called a normal plane, blah, blah, blah. And the names comes from the Latin osculum, means kissing. So osculum, not oscillating kind of thing. It's a kiss. It's the plane that comes closest to the containing the part near the P. So whatever is the closest to the curve, that's the kissing plane. That's important. Why you keep doing that? Today you're just glitching. I can see that. Finally, let's see. Here's a nice applications. Applications with graph. You don't have to write this down either. That's mostly, you will see it in your homework. The circle that lies on the oscillating plane has the same tangent as C, and it can concave side and blah, blah, blah. So you can actually figure out the curvature of something using the circle, and T is the one that touches the curve, and it's perpendicular. So it gives you lots of information. I think that's the one I wanted to show. Let's see. Oh, this one. Yeah, look at that. Pretty cool. So those three vectors that describe everything. How fast it changes, the curvature, the tangents basically tell you everything. So tangent vector in green, normal vector in yellow, oscillating vector blue, and osculating circle. Okay, I have that. Let's see, what is that? Oh, this one is even prettier. So this one I liked a lot because it also has those T and B vectors, but then you see a circle. What do you think that this circle is describing? Why there's a circle there? It describes the curvature. The bigger the circle, the smoother this 3D curve is. So if it's a spring or DNA, a helix, right? If it consists of huge circles, then the helix will be going slowly. If it's small and goes fast, then it will have small circles. So the radius of the circle gives you the curvature. And this is described by T and B. T and B are touching the circle, just like on this picture. This is called osculating circle. Osculating means kissing circle. So it gives a kiss to a curve. It's touching it. Osculating circle. That circle describes how curved something is. The big radius means it's pretty smooth. The small radius means it's oscillating a lot. Oscillating, I guess. Finally, let's do the example. Yes. Let's do this example. Let's see if it's this one I want to do. Yes. This will help you with your homework. Example, find the unit normal vector, unit binormal vector for the circle. They usually skip saying find the unit tangent vector because you have to find it anyways to find a normal. But basically find T and B. Find T and B. So I have videos on that. I clearly remember that I have videos on this these homework problems. On vectors for the circle helix. These vectors tells you lots of information, how the helix is spinning, does it have big spins, small spins, blah, 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 and also which direction they're going, and so on. R is given, cosine T, sine T, and T, very classical one. Is this the one? Oh yeah, here it is. See, it's like literally what we're talking about. find those three vectors because they're describing lots of things. You see the normal vector is pointing towards the middle, so that's also kind of really cool ideas here. So solution. You just need to know all the formulas. So maybe start with that. Formulas. Formulas are, you need to find, it says find n normal vector, but so skip some space, right? Normal vector, the unit normal vector, requires you to find unit tangent vector. So you'll have t prime over t prime size. So to find that, I need to first find t. That's a tangent unit tangent vector. That is r prime over r prime size. To find that, guess what you need to find first? R prime. So it's all going back to the original r. Vector, 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 vector. And then b, when you find all of this, you think you're done? No, now you do cross product. And you do cross product of the two previous one. T and n. T cross n. Like so. Like so. Maybe I should do a separate video for that so you can find it easily for your homework. I just realized.